Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And in this hour, we're going to throw the lines open because this hour is your hour. Okay, well, without any further ado, let's go right on to the first listener phone call.
Hi, this is Timothy. I was just wondering if we would be able to use Mars as a substation to reach the outer limits of space. Thank you.
Well, you ask a question that is one of the hot topics in NASA right now. As you realize, in the last 5 years, people criticize NASA for being the agency to nowhere, the agency that has nowhere to go, the agency that boldly goes where everyone has gone before. Well, last year they finally laid out a sequence of events for the ultimate mission, a manned mission to Mars by 2030 at the earliest. The first stage is in 3 stages. The first stage of this 3-part mission to Mars would be to test the booster rocket and the payload, the Orion spacecraft. So in the first stage, they're going to continue testing of the SLS heavy booster rocket, sufficient to carry a manned crew to Mars, and the Orion spacecraft, which will actually house the astronauts. That's step 1. In step 2, they're going to go to the asteroid belt. They're going to pick a nearby target, perhaps a passing asteroid, and send our astronauts to perhaps land on it. And so we're going to be making the first extraterrestrial contact since the Apollo program of the 1960s. That's step 2. Step 3 is on to Mars. And of course, it's going to be an arduous process, perhaps 2 years, a 2-year mission to the red planet. And a number of stops in between. NASA has said that perhaps as going to Mars, perhaps a baby step would be to land on other asteroids and even the moons of Mars. Mars has 2 baby moons, Deimos and Phobos. They're probably asteroids which were captured by the gravitational field of Mars. We're not sure. And we hope to perhaps land on these because they'll act as a space station. In some sense, we already have 2 space stations circulating around Mars, Deimos and Phobos, the moons of Mars. And so some people think that perhaps we should land on them first before actually landing on the red planet. I should also point out that years ago, some Russian astronomers speculated that perhaps Deimos and Phobos, the 2 moons of Mars, were actually space stations built by Martians perhaps millions of years ago. And the reason for that, it's not so far-fetched. It turns out that if you look at the orbit of Deimos and Phobos very carefully with computers, you find that they deviate slightly from Newton's laws of motion. Now, if you deviate from Newton's laws of motion, you're in big trouble. It means that either Newton is wrong, which we do not want to believe, or perhaps something is tugging on you. Something is making you go in a slightly eccentric orbit. Well, now we have photographs, detailed photographs of Deimos and Phobos. And what do they look like? They look like a potato. They're irregularly shaped, they're pockmarked, and that perhaps can explain why the orbits are slightly wobbly. It's because of micrometeorite collisions. Because they're so small, they're pockmarked with meteor craters, and as a consequence, that might explain the reason why the orbits deviate ever so slightly from Newton's laws of motion. So anyway, to answer your question, yes, NASA has a sequence of events leading up to a manned mission to Mars, which includes visiting asteroids and perhaps visiting moons as a step toward going to the red planet. And I highly recommend you see the movie The Martian, because it is a science fiction movie that's devoid of aliens, devoid of UFOs. It gives you perhaps the most realistic sequence of what actually may happen in the coming decades, leading up to perhaps 2030 or maybe 2040, when astronauts really do encounter the red planet. Okay, let's move right along to the next listener phone call.
Hey, love Professor's show, and my name is Chris. I wanted to say, I'm calling from Tampa, AM 820. Just wanted to say, there was a show, Lucille Ball was on, I believe it was Johnny Carson, and she claimed she picked up a radio station, a Japanese radio station, during World War II. And so that show called Mythbusters, they did about an hour-long program, and they proved with scientists and engineers that was impossible. You know, I don't know if you've ever seen the show Mythbusters. You know, they've been on for many, many years and they had proved on that show that was not possible to pick up a radio station with your teeth. So, it might be something you could look up on the computer. It was Lucille Ball, and she was on, I believe it was Johnny Carson, claiming she could hear the Japanese talking and on her way to the studio to make movies and stuff. This was back in the 40s. And, so anyway, Mythbusters devoted, half or most of a show to proving that was totally impossible to pick up radio. Thank you.
Well, yes, I think a scientist would be a little bit skeptical as to whether Lucille Ball actually did pick up a radio message in Japanese. The first question is, how would she even know that it was Japanese? I mean, Japanese is not a language that you hear on television very frequently, especially back in the 1940s. So even if it was Japanese or maybe even another language, how would she even know? Second of all, it is true that the ionosphere, a sphere which surrounds the Earth, the outer layer of the Earth's atmosphere, has a propensity to bounce radio signals. In other words, over the horizon, radio signals can be heard by shortwave radio operators because the radio waves from on the other side of the Earth bounce off the ionosphere and will actually bounce several times before it comes to your shortwave. And so that's the reason why shortwave receivers can actually pick up messages from very, very long distances. But according to the story, Lucille Ball had an access to an ordinary radio. It wasn't a shortwave radio. But if it was a shortwave radio, then yes, it's true that radio waves will bounce off the ionosphere, making it possible for people to pick up messages all the way to Radio Moscow, for example. During the Cold War, I had a friend of mine who was an amateur shortwave radio operator, and he would listen to Radio Moscow and Radio Cuba, Radio Havana, regularly on his shortwave kit because of the fact that radio waves bounce off the ionosphere. Also, at different times of the day, you get better reception because the ionosphere itself is unstable, and as a consequence, certain times of the day, you can get signals much better than other times of the day. But to summarize, yes, I probably would doubt the fact that Lucille Ball actually did pick up Japanese, because how would she know that it's Japanese rather than another language? And because that she was probably not listening to a shortwave radio. Okay, well, moving right along now, let's take the next listener phone call.
Hello, my name is Ellie Dixon. I'm from Buford, Georgia, and I want to know how stars shine.
Well, you ask a very important question. In fact, I'm positive that when young people are born, they're born scientists because we're born wondering, what does it all mean? Where do we come from? Why does the sun shine? Why do the stars shine? Well, if the stars shone because they are made out of coal or oil, they would have burnt out thousands of years ago. So oil and coal will not sustain a fire in outer space. Plus the fact you need oxygen. Without air, you cannot have fire. And so that's yet another reason why the sun does not use ordinary oil and coal in order to create heat. What the sun burns is hydrogen. And it burns hydrogen in a way that is totally different than the burning of paper or coal. It actually burns hydrogen by fusing, by smashing the protons in hydrogen together to form helium. So two hydrogens can be smashed together to create helium plus energy. And the amount of energy comes from Einstein's famous equation, E equals mc squared. In fact, I once read a comic book where the hero had emblazoned on his chest E equals mc squared. So even comic book fans are familiar with E equals mc squared. So what does that formula mean? M corresponds to matter, turning into energy E very precisely by this equation.
Professor Kaku can help you with your homework. He can even help you with your kids' homework, but only if you ask.
Welcome back to Science Fantastic with Professor Michio Kaku. The phone lines are open. We're waiting for you to call that magic number, 866-323-2129. And all we ask of you is that you leave your name, the call letters of the radio station, the city you're calling from, and you're free to record a comment or question about science. And anything is fair game. Don't think that your question is going to be too stupid to put on national radio, because sometimes the dumbest questions are the most profound questions of all. When a 16-year-old boy asked himself a simple question, can you outrace a light beam? He changed world history when he solved that puzzle. That young boy was Albert Einstein, and the theory that he created was relativity, which gives us the atomic bomb, the energy source of the stars through E = mc squared, his famous equation, the creation of the universe and black holes. Not bad for a question asked by a 16-year-old boy called Albert Einstein. So if you want to get on national radio and ask a question or make a comment about science, give us a call at 866-323-2129. Okay, well, moving right along now, let's take the next listener phone call.
Hi, my name is Clinton. I'm from Georgia. I have a question about batteries. Being that so many things take batteries nowadays, and batteries have been stagnant in their growth, what is the latest scientific theories for improving the battery? Thank you.
Well, you ask a very embarrassing question, because when we think of Moore's law and computer power, we believe that computers double in power every 18 months. That's right, every 18 months, every Christmas, your computer is almost twice as powerful as it was last Christmas, and that keeps the economy going. It thrills the public, and it's such a convenience to have so much computer power right at your fingertips. But we're spoiled. Moore's law does not apply to other things other than computer power. Most things grow in power linearly, like a straight line, rather than exponentially when computer power takes off like a rocket. So the same thing with batteries. Batteries grow at a glacial pace. In fact, it was 100 years ago, over 100 years ago, Thomas Edison and Henry Ford, who were good friends, had a bet. And the bet was, would the battery or gasoline emerge as the energy supply of the future? Well, we all know who won the bet. It was Henry Ford who won the bet. But ultimately, Thomas Edison may have the last laugh. Now, when you think of solar power and wind power, you say, well, everyone's been talking about that forever. Why don't we have cheap solar and cheap wind that can compete with fossil fuels like oil and coal? Well, there's a problem. The problem with solar is not the solar cell. The problem with solar and wind is storage, the battery. When the sun doesn't shine, when the wind doesn't blow, you're essentially blowing in the wind, and you're wasting your money. So that's one of the reasons why Henry Ford beat Thomas Edison. However, now that people are conscious about energy, engineers and inventors of all sorts are jumping into the battery game. This is something they should have done 100 years ago. They're jumping into the battery game to try to create more efficient and cheaper batteries. In fact, the price of batteries goes down about 7% per year. It's an astronomical rate just in the last decade, because so many young enterprising people are jumping into this game. Now, even Elon Musk, the guy who is behind SpaceX, PayPal, and Tesla Motors, even he is backing batteries by investing in a huge project with Tesla Motors to create batteries that are usable for utilities. Just think about that. Your utilities waste energy when it's not peak summer or peak winter. But, of course, everyone demands that your power station be able to meet peak summer and peak winter electricity demands when demand is extremely high. But it's very inefficient to maintain that when it's not peak summer or peak winter. That's where these new batteries come in. These new batteries will smooth out this curve, creating efficiencies for the utility and also efficiencies for solar and wind power. And so there's no magic bullet. There's no exponential curve. There's no Moore's law for batteries. It's a slow, tedious process, fiddling, as inventors have always done, with better batteries.
This is Science Fantastic.
Great Scott. Oh, this is heavy.
There may be an infinite number of universes, but there's only one correct answer. You're listening to Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. This means you're not going to get a busy signal. You'll be able to contact us immediately by calling 866-323-2129. Leave your name, the call letters of the radio station, and the city you're calling from, and perhaps you can be heard on Science Fantastic. So be part of the fun. Why simply listen to the radio, listen to the news, when you can be part of it by calling 866-323-2129. Okay, well, without further ado, let's take the next listener phone call.
Yes, Professor. I'm a very, very big fan of yours all over TV and everything else. I've watched you for umpteen many times. But to be plain, pure, and simple to the, regular person that's not a PhD candidate in simple language, can you please describe Einstein's theory that you just went over, E equals mc squared, in the simplest form? And then another question I have to ask you, E equals mc squared, what if you take E equals mc squared times 3, multiply it with a factor, okay? Now, will that go into a different dimension or something like that? I'm just curious. So thank you for your time, Professor.
Well, that dovetails with the previous question that we have about E equals mc squared. But many people think that E equals mc squared is the energy source that drives the universe. Think of the stars. Think of the sun. There's so much energy in this universe, and where does it come from? What is the engine that drives the universe? When a star explodes and releases so much energy that it lights up the galaxy, where does that energy come from? And it comes from Einstein's equation, E equals mc squared. Now, before Einstein, people thought that matter was matter and energy was energy. And there's no relationship between them. Heat, a light bulb, all that energy is different from a rock. A rock cannot turn into light. But you see, that's wrong, because a rock can turn into light if that rock happens to be made out of uranium-235, and that light happens to be X-rays from a nuclear detonation. So it is true that rocks can turn to light via Einstein's equation. Now, the key factor is c squared. M is mass, the mass of uranium or the mass of hydrogen. E is energy, but the key factor is c squared. C squared is the speed of light times the speed of light. That is an astronomically large number. Therefore, even a teaspoon of M can blow up all of New York City if you were to somehow release it in a nuclear detonation. And so even a tiny amount of M will release fabulous amounts of energy because c squared is such a large number. Now, you talk about tinkering with E equals mc squared. It turns out that E equals mc squared also holds in other dimensions. That's right. I work in something called string theory, which is defined in 11-dimensional hyperspace. And it turns out that E equals mc squared also works in other dimensions. So when you go to other dimensions, you do not multiply by an overall factor. You cannot take E equals twice mc squared or E equals 10 times mc squared. No, E equals mc squared. And that equation is actually true in other dimensions. However, I should also point out that we have absolutely no evidence that these other dimensions exist. However, the leading theory of physics, which is string theory, which is what I do for a living, we string theorists believe that there are other dimensions, in fact, up to 11 other dimensions. Okay, well, moving right along, let's take the next listener phone call.
Hi, Frederick Moore, KFQD, Anchorage, Alaska. My question was, the expansion of the universe is accelerating. Is there some unseen mass beyond the observable universe? Thank you.
Okay, well, unfortunately, we've run out of time in this segment, so we'll answer your question after.
You're listening to Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Well, before the break, we had a call. The call came in saying the universe is accelerating in its expansion, and what is causing it? Well, first of all, if I knew the answer, I would get the Nobel Prize in Physics. In fact, several years ago, 3 astronomers actually did win the Nobel Prize for showing that the universe is not just expanding, which even kids know by watching The Big Bang Theory on CBS television, but the universe is actually accelerating. Now, remember, every high school textbook that has a section on astronomy says that, well, yes, the universe is expanding, but it's probably slowing down, so there's probably not much to worry about. Well, we were wrong. The universe is not slowing down. The universe is actually accelerating and speeding up. Now, what does that mean? Does that mean that the universe is careening out of control and will eventually expand into nothingness? Well, we don't know. In fact, we don't even know why it's accelerating. The leading theory, and it's just a theory, the leading theory is that something is pushing the galaxies apart, and it's some kind of anti-gravitational force. We think it is the energy of nothing. It's called dark energy, which is the energy of nothing. Even nothingness, the vacuum, has some energy associated with it. And this term was actually introduced by Albert Einstein. It was Einstein himself who first contemplated the fact that even nothing has energy associated with it. But he eventually thought, well, no, maybe I'm wrong. Well, now we know that Einstein's, quote, biggest blunder, introducing the energy of nothing, is perhaps the single most important driving force of the entire universe. And we're clueless at the present time as to what it is. Now, the leading theory of cosmology is called string theory, which is what I do for a living. And string theory does give you an explanation of the expanding, accelerating universe, but it's not very satisfying. You have to put that number in by hand. It does allow for the acceleration of the universe, but the amount of acceleration of the universe has to be put in by hand. And many people think that that's a little bit unnatural. And so string theory at the present time has a big question mark when it comes to the accelerating universe. And so again, if you want to win a Nobel Prize in physics and have your name splattered all over the halls of science, then try to figure out what is driving the accelerating universe. In fact, if the universe keeps on accelerating, it means it's going to get awfully cold in the universe. And maybe some people think this could be the end of the universe, that the universe will expand so much that the sky will be totally black. We won't even be able to receive light from the distant galaxies, and it's going to be very cold as the universe continues to expand into nothingness.
This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open in this hour, so why not jump in? Why not just jump in and be part of the fun? Okay, well, moving right along, let's take the next listener phone call.
Thank you for taking my call, Professor. This is Charlie, Chattanooga. 102.3 FM. My question is, when you mentioned, I think it was about 10,000 years ago, that there were 2 miles of snow in New York, let's put it that way. When the snow is on there 2 miles thick, my question is the ocean down anymore, the level of the ocean? Thank you.
Well, you hit the nail on the head, and that is during the Ice Age, because so much water from the oceans was soaked up into the ice. It meant that sea levels actually dropped. And so the map of the Earth actually changed as a consequence. And this had consequences for North America. First of all, we think that most of North America was covered by about a half a mile of ice. And so it was really cold in most of North America. And we can see evidence of this in the Great Lakes. Why do we have the Great Lakes near Chicago and Michigan? We have the Great Lakes, so that's a remnant of the ice, half a mile of ice that melted 10,000 years ago. And so that means that the coastline of the world was much different. Now, when you take a look at what the map must have looked like, you see that there was a land bridge connecting Asia with Canada going through Alaska. And we think that many peoples, Asian peoples, perhaps in Mongolia, took advantage of that land bridge because sea levels were so low. It meant that it was relatively easy to cross from Siberia across Alaska into Canada, and they became the Native American peoples. In fact, by looking at DNA evidence, we can actually trace the lineage. We can actually see that there were at least 3, not just 1, 2, but at least 3 separate migrations from the old world into the new world that took place over 10,000 years ago during the Ice Age, because so much water was absorbed into ice that sea levels began to drop, changing the coastline so that Alaska expanded in size, making it possible for this land bridge to take peoples from Asia, for example, Mongolia, and we can now trace them going into the Americas. In fact, DNA evidence is so powerful that we can actually see migrations of Native Americans and Aboriginal peoples, for example, the Polynesians. Many people gasp, realizing that the Polynesian people must have braved the Pacific Ocean in order to go to Hawaii. And by looking at DNA evidence, we know where they came from. Most Polynesian people came from Taiwan. Who would have thought? Who would have thought that Polynesian peoples are mainly Taiwanese people? In fact, I remember when I was a kid reading the work of Thor Heyerdahl, an explorer, who thought that explorers from Latin America sailed in the reverse direction and they populated Polynesia. Nope. We now have evidence from DNA by which we can actually trace island by island. We can actually see how the island hopping took place, and we can date it. We can actually give a date when each of the Polynesian islands was colonized by native peoples coming from Taiwan and going into the Pacific. Amazing. All of that from DNA analysis. Okay, well, let's move right along to the next listener phone call.
Hello, this is Keith McCabe from Hartley, Texas. I am calling you. I wrote you a letter. I hope you got it. I would like to ask you what you think of my idea of what string theory could be.
Okay, well, first of all, I have to apologize for the people who write me letters. I get hundreds of letters, and it's physically impossible to answer them, or else I'd be spending all my time plus sleeping time answering questions. So it's better for me to answer questions on radio, where I can actually interact with people directly. So instead of trying to critique people's theories, first of all, some people want to know, well, what is string theory? And so let me give you a brief description of string theory. First of all, when we split atoms apart, we find there are more particles. Hundreds, thousands of particles we get by smashing protons together with our particle accelerators. We give them bizarre names: leptons, hadrons, protons, neutrons, and all of them we think are nothing but musical notes. musical notes on a tiny vibrating string. And so chemistry is nothing but the melodies we can play on these strings. Physics is the harmonies of these strings. And the universe we think is cosmic music, the music of vibrating strings. We're going to throw the mics open, and you can ask any and all questions or make any comments about science.
Science fantastic.
Well, let's take a few listener phone calls.
Does all matter emit light?
You're on the air.
Can you tell us how many planets are out there? I believe I can answer one of the questions.
And I say to myself, oh my God, he got it right.
I've been a fan of yours for years and years.
And now you will be part of it, rocketing beyond the horizon of our time to join the greatest human adventure of all time.
Now, Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, not only do we profile some of the most amazing discoveries in science and technology, we also throw the lines open. Here's your chance. Okay, well, let's throw the lines open. Let's take the first listener phone call. Hello. This is Science Fantastic. You're on the air. Any comments or questions?
I was just curious of how the way that the dogs as in animals have evolved over the years. Did they come from wolves, or how did they all come about? And the different breeds, how are we mixing breeds and getting all these different variances of animals over the years? Thank you.
Well, you ask a very intriguing question that's being answered even as we speak by geneticists who are beginning to sequence the DNA of dogs. Well, first of all, we know that dogs were domesticated roughly 10,000 years ago. 10,000 years ago, that's when the Ice Age melted. We forget that before then, during the peak of the Ice Age, most of North America was under a half a mile of ice. Well, after the ice melted, agriculture gets off the ground slowly, civilization, villages start, and that's when we began to domesticate dogs from the wolf, Canis lupus. And that's one reason why dogs of any breed can breed with any other dog, because they're all descended from one species, Canis lupus. Now, when scientists began to sequence the DNA of dogs, they found something very interesting. They found out that there was just not one branch of lineage, but several branches depending upon where you were on the planet Earth. So in other words, not once, but many times, different populations of people domesticated the dog and then began to breed the dog for their own particular purposes. That's why we have such a bewildering variety of dogs for specific purposes. Some dogs, for example, are good at shepherding sheep. Others are hunters. Others are simply good companions. That's why we have such a multiplicity of dogs. And dogs, of course, don't live very long. Dogs age much faster than us, about 5 times faster. So you can imagine how fast evolution has taken place, that we have bred the dog for just 10,000 years. Then you can even calculate. You can even calculate roughly how many generations of dogs there have been since the very first dog. You just divide into 10,000 years. Now, not only this, but because dogs begin to be bred by humans and then we begin to interbreed dogs, that's the reason why dogs suffer from many genetic mutations. It's very sad. But if you have a dog, you begin to realize that as they age, they begin to exhibit many of the genetic mutations, their feet, their digestive system, cancers. They begin to show different kinds of genetic diseases because of all the inbreeding that took place. So in other words, man's best friend has in some sense paid a price. The benefit of domestication is that there are more dogs today than wolves. So from an evolutionary point of view, bingo. it was actually a success story for the dog because there are more dogs than wolves. But the price that dogs paid for this is that they are essentially riddled with genetic mutations, many of which begin to show themselves as they begin to age. Okay, well, let's take the next listener phone call. Hello, this is Science Fantastic. You're on the air. Any comments or questions?
My name is Eric, and I'm calling from Corpus Christi, Texas, 1440 Keys. And my question is, can we build, or have we already built, atomic-powered aircraft? I'm wondering if this aircraft could maybe describe what we've seen in the skies and don't have a true idea of what it is. And I'm wondering if maybe this might be the atomic-powered aircraft might be what we're looking at.
Well, Eric, you ask a very interesting question because my advisor when I was young, starting in high school, was Edward Teller. Edward Teller was the father of the hydrogen bomb, and he was a very vocal proponent of putting nukes everywhere. Nukes not only to carve out canals between continents, but also nuclear power plants in aircraft carriers, submarines, rockets, and airplanes. So let me tell you a little bit about the secret history of this, which is rather interesting. Back in the 1950s, the United States military and government very seriously looked at the possibility of putting nuclear power plants, not just in submarines, which was a smashing success, but also in rockets and airplanes. In fact, there was a project called the Kiwi. The Kiwi is a flightless bird, and was aptly named because it was basically a nuclear rocket on a railroad track. So when you threw the switch, the ignition took place. All of a sudden, you had all this exhaust coming out one end, and the nuclear rocket would go barreling down the railroad tracks. Well, there were some problems. First of all, the reactor tended to be unstable. It tended to melt down. There were problems with maintaining the reactor, and the military eventually gave up. They said it's simply not worth it. For the cost-benefit analysis, they're simply not getting the bang for the buck. And the same thing for the airplane. It turns out that, yes, in principle, you could put a nuclear power plant in an airplane, and the airplane could go around the world many times. But simply refueling a jet, turned out to be much more cost-effective, not to mention the fact that if the rocket crashed or if the airplane crashed, you would have a nightmare. Can you imagine a nuclear power plant landing in someone's backyard? The contamination would be enormous. And in the 50s and 60s, the military had some experience with this because there were several broken arrows during that time. An arrow is jargon for a nuclear weapon. A broken arrow is a bomb that literally falls out of the bomb bay of a bomber. There have been a number of incidences where atomic bombs accidentally landed on South Carolina, North Carolina, off the coast of Georgia. And this, of course, was a huge embarrassment for the military. So we actually did have nuclear materials literally falling from the sky in terms of nuclear bombs. So, again, some people think that maybe, just maybe, flying saucer sightings are actually secret military craft. Well, who knows? We do know, however, that the military deliberately led the public to believe that sightings of the stealth bomber may in fact have been UFOs to cover up the fact that the military was experimenting with stealth bombers or bombers that can deflect and diffuse radar so they don't have much of a radar signature. But basically, the reason why the atomic airplane was shelved was because it was not that safe, it was unstable, and basically not that cost effective. Simply refueling would give the range needed for airplanes to go pretty much around the world. Okay, well, let's take the next listener phone call. Hi, this is Science Fantastic. You're on the air. Any comments or questions?
This is Jessica from Corpus Christi. I'm listening to station 1440 AM. And my question is, who was the first person to think, like, okay, I'm going to eat whatever comes out of this chicken's butt? Well, basically I'm talking about an egg. But, like, What is that?
Okay, well, let me try to take a crack at that question. I think your question is in two parts. First of all, who was the first person to have a light bulb emerge over their head and say, oh, gee, that looks pretty delicious, an egg. Maybe I'll grab that egg. And then, of course, everybody wants to know which came first, the chicken or the egg. Well, let me take a stab at it. First of all, the first person to look at an egg and decide to eat it was probably not a person at all. We descended from the apes, according to the theory of Charles Darwin, and apes eat eggs. In fact, if you go even further back in time, mammals were once reptiles. Mammals, in fact, are an offshoot of the reptiles, and reptiles eat eggs as well. So the answer to your question is very simply, there was no first human who looked at an egg and said to themselves, well, gee, this is a great meal, because it goes back even before humankind was born. If you go all the way back, even primitive animals will eat eggs of other animals. And then the other question is, which came first, the chicken or the egg? And the answer to that is probably neither. The chicken and the egg probably emerged from a more simpler form. You realize if you go way back into the past now, 2 billion years into the past, you just had microorganisms on the planet Earth that simply underwent mitosis, that is, splitting apart. It took billions of years for these germs, these bacteria, to create concrete organisms that then began to lay eggs and then began to differentiate. So to answer your question, there was no first human who spied the first egg. And which came first, the chicken or the egg? The answer is probably neither.
Science Fan. You're listening to Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, it's Open Mic on Science Fantastic. Okay, well, let's take the next listener phone call. Hello, this is Science Fantastic. You're on the air. Any comments or questions?
Hi, my name is Daniel Hensley, and I am calling from Pensacola, Florida. And I am talking from News Talk 1370, WCOA. My question is, spirits and everything, are they really matter? Like ghosts, can they actually become matter, or are they just like something of your brain?
Okay, well, you ask a very ancient question that goes all the way back to the dawn of civilization. Take a look at any mythology from any society, and you'll see myths of spirits and ghosts and stuff like that. Well, as a scientist, we can only say a few things. Science is based on what is reproducible, measurable, and testable. That's the foundation of science. If you have a scientific result, it has to work all the time. It just can't work on Tuesdays or Thursdays, but not on Wednesdays. It has to be eternal. Well, when it comes to ghosts and things, we find a problem, and that is they're not reproducible. They're not testable. In fact, they're not even falsifiable. How can you prove or even disprove the existence of ghosts, demons, and spirits? So scientists are kind of at a loss at this point. However, that doesn't mean that some scientists haven't speculated about these things. So let's mention two possible speculations. One speculation, as you mentioned, is that they are perhaps figments of the imagination. Another is maybe they're from another dimension. If they're a figment of our imagination, then it turns out there should be a part of the brain which induces this kind of behavior. In fact, there is. It's called epileptic lesions. In fact, we've had guests on radio talking about this. It turns out that a certain lesion to the brain, a stroke, an injury, a blow to the brain, will actually set off these epileptic lesions, in which case you feel that you're in the presence of a spirit. Anything that happens, you think that something is behind it. These people, for example, when they're interviewed in hospitals, say that when it rains, it's because there are evil spirits that are punishing you. that if you fall down, it's because you did something bad that day. So any event that happens, there's intentionality, evil, or a spirit behind it. And you can even induce this with radio. It turns out there's an electromagnetic transmitter. Time Magazine even did a story on it, where if you shine this radio to a certain part of the brain, you can actually induce this effect so that you feel like you're in the presence of a ghost or a spirit. Richard Dawkins, who I met a few months ago in Mexico at a conference, he's an atheist from Oxford University, a leading atheist, so some people had the bright idea of putting him in this contraption. So they put radio waves into his brain to see whether or not this confirmed atheist would say that, yes, there is a God. Well, after Professor Dawkins came out, he said, nope, I didn't see any ghosts at all. However, there is another theory that says that maybe ghosts are from another dimension. Let's say that you have a tabletop where there are people living on a tabletop, flatlanders that are squashed in 2 dimensions. If you are standing above the table looking down, then the flatlanders cannot see you. You are invisible. But you could perform all sorts of magic tricks. You could put your finger right through the table, the surface of the table, and the beings on the table would see a sphere, a circle of flesh as you stick your finger in it. You'd be able to peel these people off the table and make them float, so they would disappear off their universe, and you can put them back. So in other words, if we are nothing but flatlanders living in a flat universe, then somebody from a higher dimension could disappear, reappear, reach into our stomach, perform surgery without cutting our skin, and do all sorts of magic feats that are usually associated with ghosts. Well, I don't know. All I'm saying is that theologians have written about the possibility that maybe ghosts live in a higher dimension. Many of my books, like Hyperspace, talk about the lore that goes back. But, hey, I'm a scientist. I won't believe it till we can reproduce it in the laboratory.
This is Science. Now, Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, once again, it is open mic. Hello, this is Science Fantastic. You're on the air. Any comments or questions?
Jim Sanders, Pensacola, Florida, listening on WCOA Radio 1370 AM. If the Big Bang happened 13.5 billion years ago and things are rushing away from that point, then isn't there a whole lot of nothing between that point and the edge where we are expanding away like a big bubble?
Okay, well, you ask a question that a lot of people ask when they first hear about the Big Bang Theory. If the Big Bang means that eventually we came from a point, and we are 13.7 billion years away from that original point, then first of all, where is that point? Is it in the constellation Virgo, the constellation of the Big Dipper? Where is that point? And are we spinning away from that point at a very fast velocity? And as you point out, is there a gap? Well, think of a balloon. Think of a balloon, and we are like flies on flypaper. We're trapped on the surface of the balloon, and the balloon is expanding in all directions. Okay, got that? Now, if you ask, let's say, an ant walking on the surface of this balloon, where did the balloon originate from? Where was the original expansion taking place? Well, the ant would say, well, nowhere. Nowhere on the surface of the balloon did the expansion take place. The balloon is expanding away from the point of origin. So, in other words, the Big Bang, in some sense, happened everywhere and nowhere. There is no point on the surface of the balloon that is the origin of the Big Bang. So if you ask the ant, then where did the expansion take place? The answer would be, well, it's off the surface of the balloon. But since the surface of the balloon is everything there is, the whole universe is the surface of the balloon, then the Big Bang took place off the surface of the universe. In other words, in hyperspace, in another dimension. So that's the simplest way to realize that you cannot point to one particular point in the night sky and say that's the point of the origin of the universe. So if you were around 13.7 billion years ago, what would you see? Back then, the universe would be very small, smaller than a bowling ball, smaller than a ping pong ball, smaller than an electron. And as it expanded, you would ask a question, well, where is the Big Bang? And the answer would be everywhere. Everywhere you look, you would see radiation. It'd be very hot, quite radioactive. Everywhere you look, you would see essentially the origin of the Big Bang. Now, you may say to yourself, if it's that abstract, then how do we even know it's correct? Well, we have photographs of the Big Bang. Pictures, baby pictures of the infant universe. Go to nasa.gov and look under WMAP, W-M-A-P. That's a satellite which is photographing the explosion itself. Believe it or not, the explosion is still reverberating around the surface of our balloon. So let's say the balloon is expanding, but there are ripples on the surface of the balloon because the origin was so violent that it created shock waves. Well, we can photograph these shock waves, and by golly, it looks like an explosion. This is called the famous microwave background radiation. The radiation of the Big Bang is quite cold now. It's in the microwave range, 3 degrees above absolute zero, and you can photograph that radiation. And in fact, when you have a radio or TV and you get that static on your radio, some of that static actually comes from Genesis. So believe it or not, you are actually listening to creation itself. The static, that buzz you hear on radio, some of it comes from Jupiter. The planet Jupiter emits a lot of radiation, but a lot of that radiation also comes from the origin of the universe itself. Okay, I think we have time for another listener phone call. Hello, this is Science Fantastic. You're on the air. Any comments or questions?
Jonathan, I am calling from Inglewood, California. I'm listening to you on Freedom 970. And I don't think that time exists. Can you tell me whether or not you believe it does?
Well, some people say space, time, maybe it's all an optical illusion. Maybe time doesn't really exist. Maybe space doesn't exist. Well, that's when we have to define things, because without definitions, we're just spouting words into the vacuum. And, well, when you define time, you realize that time is a way to measure change. When things change, we need a way to measure that change, and we call that time. So obviously things change. The very fact that you could even ask that question is a consequence of the fact that your muscles can move, your mouth can move, and the radio waves can go across space, and I can listen to it. So the very fact that there is change means that there is time, because time is nothing but a way that we have of measuring change. Now, Shakespeare, I think, had the best way of looking at it. Shakespeare said that the universe is a stage. Everything around us is nothing but a stage, and we are actors making our entrances and exits on the stage of life. Well, this stage is space. We are matter propelled by energy, and the way in which you measure change along the stage of life is time. Now, of course, things get very complicated when Einstein comes along, and he shows that there's really a four-dimensional structure, that is space and time are really, in some sense, part of a single fabric, a fabric that can stretch and bend. So in other words, not only is there time, but there's also space, and that space and time are part of a larger entity called space-time. Matter and energy are also part of a larger concept called matter-energy, and that's the relativistic way, the Einsteinian way of viewing the universe.
This is Science Fantastic. This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Well, let's take the next listener phone call. Hello, this is Science Fantastic. You're on the air. Any comments or questions?
Hi, this is Steve. I'm calling from Tucson, Arizona. I know that hair on our body is essentially a dead organism. When you cut a hair, there's no nerve. Yet hair seems to know how long to grow. The hair on my arms does not grow as long as the hair on my head. If I shave the hair on my arm or leg, it only grows back a certain length. How does the hair know how long to grow? Thank you.
Well, Steve, you ask a very interesting question, which had enormous commercial implications because, of course, as baby boomers age, they lose their hair, specifically on the top of their head. And so baldness is going to be one of the targets of biotechnology. In fact, recently it was announced that we're unraveling some of the genes of baldness, and that in turn could give us real, not fake, but real cures for baldness. Well, first of all, let's talk about what is hair. Hair, believe it or not, is protein. As you pointed out, it's not alive in the usual sense of the word. It is protein, not the kind of protein that builds muscle, but nonetheless a form of protein. And hair, left to itself, will simply grow infinitely long. There are certain peoples who don't cut their hair, and their hair grows on to be very long. But hair also falls out, and that's why certain hairs on your arm and places like that don't simply get longer and longer. It's not that the hair suddenly shuts itself off. The hair falls off, and new hair grows, and it gives the illusion that the hair suddenly knows when to stop.
You're listening to Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. Okay, well, let's take the next listener phone call. Hello, this is Science Fantastic. You're on the air. Any comments or questions?
My question is, why can't NASA use old technology that's been proven from the 70s and a design that is ultra-safe and ship some of this nuclear waste out towards the sun, charging, of course, the nuclear power companies a high premium, not only in America, but in France, in Germany, and where they're having all these problems with the nuclear waste, make their own money and therefore turn that money over and fund missions that they would like to run but can't because they can't get money from the government.
Well, you ask a question that actually has some very deep answers to it. At first, it sounds like a no-brainer. Nuclear power plants generate nuclear waste, so why not simply send it to the sun? The sun is the ultimate garbage can, right? Well, there are some very big practical problems which have prevented this from happening. First of all, booster rocket failure takes place about 1% of the time. That's right. When our brave astronauts don their spacesuits, they know that 1% of the time they may not come back. These are former fighter pilots, former military people. A lot of them know the risks of going into space. If you calculate the number of disasters, for example, on the space shuttle, we've had 2 horrendous accidents, each one killing 7 brave astronauts, then the odds came out pretty much right on the dot. 1% of the time. 1% of the space shuttle shots and ended in tragic failure. Now, you can imagine what would happen if nuclear waste were on one of these rockets. Sure, you're right. Many of the shots would go to the sun. We can do that. So you say to yourself, well, why not send all the waste into outer space? Well, there's several problems. One, of course, is booster rocket failure. 1% of the time, as Isaac Newton said, what goes up comes back down, usually on somebody's backyard. And the ecological implications of that would be horrible. Can you imagine a Chernobyl from outer space spewing all the radioactive waste? But there's also a more mundane practical problem, cost. It costs about $10,000 to put a pound of anything into orbit. Forget going to the sun. We're just talking about spinning wheels around the Earth. $10,000 $10,000 per pound. Get on a bathroom scale and weigh yourself. Well, if you're made out of solid gold, if your body were made out of solid gold, that's the cost of what it would take to put your body into orbit, $10,000 a pound. Now, to send it into the sun would cost more like $100,000 a pound to send it into the sun. So you see, there's some real problems with regards to cost. And then, of course, you have the other problem, the sheer amount of nuclear waste. Every reactor produces about 30 tons, not pounds, 30 tons of high-level waste per year. And the United States alone has about 100 reactors. So do the math. 100 times 30 tons per year, and you realize the enormous amount of nuclear waste just generated by the United States alone. And France, hey, something on the order of 70% of their electricity in France comes from nuclear power. So you know that the French have an even larger commitment to nuclear energy than us, and that means an enormous amount of waste. And how long do we have to guard it? Tens of thousands to millions of years. That's incredible. The half-life of uranium-238, for example, is 4.5 billion years. That's the age of the solar system. The age of the solar system is the half-life of uranium-238. Now, by law, the United States government has stated that radioactive waste should be sequestered from the environment for 10,000 years. That's why in Yucca Mountains outside Las Vegas, we were going to put our nuclear waste. But the Yucca Mountains site has been canceled by President Barack Obama. Why? It's unstable. 10,000 years ago, we had an ice age, for God's sake, an ice age. How do you predict these things? How can you make sure that nuclear waste does not encounter ice and flooding over a 10,000-year period of time when the last 10,000 years, most of North America was under a half a mile of ice? Well, the headache proliferates on and on. Now, we physicists have thought about all these things. There's even an issue of the Journal of Modern Physics, which goes through the options. Another option was to put it under the seabed, inject it directly into the tectonic plates. Well, that sounds like a great idea. Tectonic plates are stable for millions of years, so why not simply shoot the waste beneath the plates? Well, the conclusion of physicists was that we know not that much about earthquakes and the surface of the Earth. We know even less about the bottom of the ocean. So injecting nuclear waste on the bottom of the oceans would be a nightmare with unpredictable results. Yet another possibility was shoot it in salt domes. Well, we tried that in Lyons, Kansas. Kansas was supposed to be the site where we would put nuclear waste, but then it turns out that we didn't know that the Lyons, Kansas was used by wildcatters, and there's like holes drilled by them that have unknown locations. It's like pockmarked, like Swiss cheese. Well, as you can imagine, for all these reasons, we simply don't know what to do with the waste.
Now, Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And in this hour, once again, we're going to throw the lines open because this hour is your hour. Okay, well, moving right along, let's take the next listener phone call.
Yeah, listening from Northeast Pennsylvania, WILK, and the sun will interest me the most. How it keeps, where the energy comes from, how it keeps shining, the diameter, and if it shines on the backside also. Thank you very much. Bye-bye.
Okay, well, the sun does not shine on the backside. It shines uniformly throughout the entire sphere, and it does so because of a process called fusion. In other words, hydrogen gas, which is what the sun is basically made out of, is compressed evenly on all sides by gravity, and as it compresses, it heats up in temperature, just like the opposite of your refrigerator. When you expand the gas inside the coils of your refrigerator, it gets cold. When you compress gas, it gets hot. So that's what happens to the sun. Gravitational pull turns gravitational energy into heat. When you hit several tens of millions of degrees at the center of the star, protons are slammed into protons and hydrogen, creating helium. And so the fusing of hydrogen into helium creates energy via E equals mc squared. So m is a tiny bit of hydrogen which turns into energy. E is energy, and c is the speed of light squared, which is a humongous number. That's why even a tiny bit of uranium will unleash the atomic bomb. So a piece of the sun, no more than a teaspoon, has enough energy in it to devastate all of New York City. That's the power of the sun. Now, if you were to think that the sun shines because of oil or coal, you would have a problem. First of all, there's no air out there, so there's no oxidation of coal or oil to heat up the sun. And second of all, you can also show that even if there was oxygen out there, it would be exhausted in a matter of just a few hundreds or a few thousands of years. And yet the sun has been burning for 4 to 5 billion years. And so a new force is involved, not the force of fire, but the force of nuclear fire. And that force is unleashed by Einstein's E equals mc squared. Okay, well, let's move right along to the next question.
Hi, Dr. Kaku. This is Peter Kleiman. Glad to talk to you again. Once again, I just had a question on physics. My question is, why is the speed of light not something faster or slower? Why is c the number value that it is? Is it different in other universes? Is it the same across the whole entire multiverse? Why is it a certain value? Thank you for letting me ask a question. Thanks. Bye.
Well, you ask a question which is quite embarrassing for physicists. The short answer is we don't really know. Einstein simply starts with the speed of light being what it is, and then he probes the consequences of that fact. But then you can run the videotape backwards and say, now, wait a minute. Where did that first assumption come from? Where did the speed of light itself comes from? And the answer is we don't really know. However, in our universe, we think that the speed of light is a constant, just the way Einstein predicted. When we look at radiation, light radiation coming from the distant galaxies at the very edge of the visible universe, we find that the laws of physics and the laws of optics are the same, exactly the same. We don't see any difference at all. So this distant galaxy could be next door, and the radiation that we get from them would be very similar. And so we see no change in the laws of physics in this universe. However, you ask another question, and that is there a multiverse of universes? And in these other universes, can the speed of light be different? And the answer to that is, well, maybe. First of all, I work on something called string theory, which we think is a successor to Einstein's theory of gravity. We think it is the leading candidate for a theory of everything. In fact, if you saw that Oscar-winning movie, The Theory of Everything, the one problem with that movie is they never told you what the name of the theory is. They simply talked about Stephen Hawking's life and his ailment. Well, the theory is called string theory, and that's what I do for a living. And string theory says that our universe is a bubble floating in a much larger arena of hyperspace, in fact, 11-dimensional hyperspace, but there could be other bubbles out there that once in a while bump into our universe. Now, when these universes bump into each other or fission off and peel off a baby universe, the laws of physics can change. And so we have a multiverse of universes such that each universe has its own string theory. In other words, the different constants of nature, including the mass of the electron, the speed of light, things like that, may actually be different. The laws of physics may actually be different in these other universes. Now, can we prove it? Well, the Europeans think we might be able to have a handle on this question. They plan to launch LISA into orbit in the next 20 years. LISA is the Laser Interferometry Space Antenna. It is designed to pick up gravity waves not on the Earth. We've done that just a few months ago, gravity waves on the Earth, but gravity waves in outer space. Gravity waves emitted not from colliding black holes, we did that just a few months ago, but gravity waves from the creation of the universe itself. And that should give us radiation from the pre-Big Bang universe. And then we can have numbers, real measurable numbers, to answer the question, are there different laws of physics in other universes? So the short answer to your question is we don't know, but it is room for experiment, and the European Space Agency will send satellites into outer space to measure gravity waves from the Big Bang, and that should give us a clue as to whether or not other universes can exist. And then, of course, everyone wants to ask the last question, is Elvis Presley still alive in another universe? Well, if the speed of light can change in other universes, then, yeah, there's always a chance that the king could be alive in another universe. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Okay, well, moving right along, let's take the next listener phone call.
Hi, Professor. This is Tony calling from Jasper, Florida. My question is, if two spaceships are moving toward each other at 186,000 miles per second, the speed of light, what is the total impact of the collision? Is it 186,000 miles per second, or is it double? Thank you.
Well, you ask a question that the young Einstein asked himself when he was 16 years old. You see, if the speed of light is a constant, that means that all sorts of bizarre distortions take place. First of all, if you're coming at an object at near the speed of light and it's coming at you near the speed of light, then common sense tells you that the relative velocity is twice the speed of light. Or let's say you're in a train that's speeding near the speed of light and you have a flashlight. You light the flashlight in the direction of motion of the train. Since the train is moving at the speed of light and the light bulb is emitting light at the speed of light, then an outside observer would say that the light beam is moving at twice the speed of light. Wrong. We've done this experiment. It is always according to Einstein's theory. Velocities do not add. That's the simple question. In fact, there's even a mathematical formula that shows that if you're moving at the speed of light or near the speed of light, and you're moving in a train that's moving near the speed of light, the sum of the two is not twice the speed of light. You have to divide by a certain relativistic factor. Now, how is it possible that an object can seemingly have two different velocities depending upon who measures it? And the answer is that a man inside a rocket ship, his brain slows down relative to somebody looking at the rocket ship. So let's say you have a rocket ship traveling near the speed of light, and you turn on a flashlight. By rights, the flashlight should be going at twice the speed of light, but it isn't. It always moves at the speed of light. Now, you may tear your hair out saying, how's that possible? And the answer struck Einstein in a streetcar in the spring of 1905. He was thinking about the clock tower, the famous clock tower in Bern, Switzerland, as the streetcar was leaving, and he asked himself a question. If this streetcar were moving at the speed of light, what would I see when I looked at the clock tower in Bern? Then he got it. He said that a storm broke in my mind. And that is, the person inside the train, his brain slows down because time itself slows down in the rocket ship. Every time he tries to measure things, it always comes out that the speed of light is exactly the same, no matter if the light beam is moving toward you, the light beam is moving away from you, or the light beam is moving at an angle with respect to you. Now that violates common sense. Everything in your fiber, everything in your experience tells you that velocities add. Well, wrong. The universe does not believe in your common sense. The universe says, nope, that's not true. The speed of light is a constant no matter how you measure it in any frame. And we've done this. Time and time again, we've sent rockets, ships into space, airships. Each time, the speed of light comes out exactly the way Albert Einstein said. In fact, your GPS system in your cell phone, in your pocket, depends on this. If Einstein were wrong, all GPS systems on the Earth would fail, because time does beat at a different rate for GPS satellites orbiting the planet Earth. And so you say to yourself, well, that violates common sense. The answer to that is tough. Sorry about that. The universe does not obey your common sense. Welcome back to Science Fantastic with Professor Michio Kaku. Once again, the lines are open. Okay, well, let's move right along to the next listener phone call.
Yes, this is Jimmy. Ever since I was a kid and I learned about the men walking on the moon, I wanted to be the first human to walk on Mars. And so as I grew, I took studies that direction, and I learned that we could grow oxygen and that we can grow water. But one of the largest stumbling blocks was the electromagnetic field of Mars was too weak to maintain an atmosphere. And my question is there a way that we can create a stronger electromagnetic field for the planet? Thank you. Bye.
Okay, well, Mars has been in the news ever since NASA said that, yes, we are going to Mars sometime after 2030. But the question is, why is Mars such a barren, bleak place? Well, it has very little atmosphere. Atmospheric pressure is 1% that of the Earth, and it's basically made out of carbon dioxide. But why? Why did Mars lose most of its atmosphere and, as a consequence, lose most of its liquid water? Because once upon a time, there were liquid oceans on the surface of Mars. And the answer you correctly pointed out is that Mars has almost no magnetic field. A magnetic field is very useful because it acts like a shield protecting you against the solar wind. The solar wind is very faint, but it buffets the atmosphere of every planet and blows a lot of the molecules into outer space. So because Mars has almost no magnetic field, it has no protection against the solar wind, which in turn blows the molecules of the atmosphere into outer space, causing Mars to lose 99% of its atmosphere. Now, let's say we terraform Mars. Let's say somehow we're able to raise the temperature of Mars and inject methane and other kinds of greenhouse gases and raise the temperature of Mars. The question is, won't we lose the atmosphere again? Isn't it basically a pointless exercise in futility to try to terraform Mars when the atmosphere is going to be blown off anyway? Well, yes and no. First of all, even if you create an unstable atmosphere of Mars, it's good for a few thousand years. So in other words, yes, we can create with tremendous expense an atmosphere for the planet Mars. It would cost hundreds of billions to trillions of dollars, but it's going to be stable for thousands of years. Then, thousands of years later, you'll probably have to do it again because, of course, the atmosphere, the newly formed atmosphere, will gradually leak out. But there's also another factor involved. If you raise the temperature of Mars sufficiently, it means that the polar ice caps will begin to melt because they're made out of dry ice and ordinary ice. And as the polar ice caps thaw out, it releases more greenhouse gases into the atmosphere, which accelerates the heating of Mars. So we have another effect taking place, a runaway greenhouse effect. The warmer Mars gets, the more the polar ice caps melt, releasing more greenhouse gases into the atmosphere, which raise the temperature even more. So there is room for hope. Even though it may cost upwards of $1 trillion to initiate this process, once it starts, it generates enough heat to sustain it for thousands of years. Welcome back to Science Fantastic with Professor Michio Kaku. Once again, the lines are open. Well, moving right along now, let's take the next listener phone call.
Hi, my name is Solomon. I'm calling from Wilkes-Barre, Pennsylvania. 103.1 FM is the station I'm tuned to. My question to Professor Michio Kaku is that in most explanation of gravity and most depiction of what gravity look like, they show us a fabric and whatever objects that are pushing down on it causing gravity. My question is, if there is no up or down in space, how does gravity indent space-time like a fabric? It just doesn't make sense to me. If you could please explain that.
Okay, well, you ask a question that a lot of people are asking, and that is, we have this picture that space-time can be viewed as a fabric like a trampoline net. So think of a trampoline net and then drop a bowling ball in the middle of the trampoline net, and the bowling ball, of course, sinks. Then you take a marble, you shoot a marble along the trampoline net, and lo and behold, my God, it orbits. It goes in a circle. The marble goes in a circle around the bowling ball. Why? Because the fabric of the trampoline net is bent. Now, this is an explanation of how gravity then warps the space-time around the Earth, and that's why the Earth goes around the sun. That's why you are sitting in your chair right now. Why are you sitting in your chair? Most people would say you're sitting in your chair because gravity is pulling you down. But Einstein says, nope, that's not why you're sitting in your chair. You're sitting in your chair because the Earth is warping the space-time around your head, and it is pushing your head into your chair. In other words, gravity is a push and not a pull. There is nothing pulling you down like gravity toward the center of the Earth. Space is pushing you down into the Earth. Now, what this questioner asks is, the analogy. Isn't the analogy wrong? Because the analogy itself requires gravity. Gravity pulls the bowling ball down into the trampoline net. So, aha, it's circular. I got him. I show that Einstein's theory is wrong because it uses gravity to explain gravity. Well, just remember that it's only an analogy. Perhaps a better analogy would be as follows. It was Shakespeare who once said that all the world is a stage, and we are like actors and actresses making our entrances and exits on the stage of life. Well, now imagine that the stage, this empty arena called space-time, is warped. And as you walk across the stage, it is impossible to walk in a straight line because of the warping of the stage. Or take a sheet of paper, crumple the sheet of paper and put an ant on the sheet of paper and ask the ant to move in a straight line. The ant cannot. It's buffeted to the left, buffeted to the right. Now put the sheet of paper in outer space. Now there's no gravity. There's no gravity. And then you ask the ant, can you move in a straight line? And the ant would still say, no. I try to walk in a straight line, but every time I try, I hit a fold, and I go to the left, I'll go to the right. So in other words, the thought experiment of Einstein is correct. The curvature of space gives you the illusion of a force. But the analogy of the bowling ball, the analogy of the trampoline net, uses gravity, and so it is slightly defective. A better analogy would be to put the sheet of paper into outer space and put an N on that sheet of paper, and then you are not referring to gravity at all to explain gravity. Welcome back to Science Fantastic with Professor Michio Kaku. Okay, moving right along, let's take the next listener phone call.
Hi, Dr. Kaku. This is Alan from Denver, Colorado. And I had a question about life on Europa or any moon surrounding Jupiter. The question is, would Jupiter's magnetic field shield the moons from solar radiation? Because as we know, on Earth, we need our magnetic field or life couldn't exist. Would that same shield exist for the moons of Jupiter? Thank you.
Well, it turns out that our space probes, as they approach Jupiter, sometimes they're overwhelmed by this barrage of radiation. Jupiter is quite radioactive. And in fact, when you turn on your TV set and you see that snow when you're between channels, especially with the older TV sets, where does that snow come from? Believe it or not, much of it comes from Jupiter. That's right, Jupiter is a gigantic creator of electromagnetic disturbances, and it also has a magnetic field. Now, as you correctly pointed out, a magnetic field can protect you against the solar wind. Think of Mars. Why is Mars a frozen desert? Mars is a frozen desert because it's lost most of its atmosphere due to the solar wind. Because Mars has no magnetic field to speak of, it has no shield to protect itself against the harsh ionizing wind that comes from the sun and blows the remaining atmosphere of Mars into outer space. So the question is now, Jupiter has satellites going around it like Europa. We think that Europa has a liquid ocean underneath the ice core. How do we know? Because of tidal forces. Tidal forces are enough to generate heat, volcanic heat, at the center of Europa, hot enough to melt the ice cover of Europa, creating an ocean. In fact, we've estimated the size of that ocean, and it's actually in volume larger than the oceans of the Earth. And the Earth, of course, is much bigger than tiny Europa. And so then the questioner asks the comment, the solar wind, is it deflected by the magnetic field surrounding Jupiter? Well, I think what the questioner is getting at is any life form on Europa protected from the solar radiation? And to some degree, yes. To some degree, Jupiter's magnetic field acts as a shield protecting Europa. However, Jupiter itself has a tremendous spray of radiation emanating from it, and so I don't think it's much of a consolation prize. In other words, any life form on Europa will have to live underneath the ice cover because the radiation from Jupiter is quite intense. So yes, Jupiter does deflect some of the solar radiation coming from the sun, dampening the radiation that would hit a moon of Jupiter. But that doesn't mean that life forms on Europa are let off the hook, because Jupiter itself generates a tremendous amount of radiation. Okay, well, let's move right along to the next listener phone call.
So my name is Tom. I'm calling from St. Petersburg, Florida, on 8:20 a.m. news. My question is regarding the phenomenal Philadelphia experiment. We've seen the documentaries. I've seen the documentaries, quite impressive. And we've seen the movies, part 1 and 2. The government officially denies the existence of time travel, but some scientific factors prove otherwise. Now, what exactly happened with the Philadelphia experiment back in 1942, 1943, when they tried to hide shit from the enemy, and they happened to get really well hidden and disappearing? Thank you.
Well, you ask a question that I often get on email, and that is, what about the Philadelphia experiment? As you correctly pointed out, it's a Hollywood movie, a movie in which scientists from World War II experiment with electromagnetic radiation on a battleship and accidentally sent the battleship backwards in time. Well, let's go back to the origin of the story. It goes back to the year 1955. In the year 1955, Albert Einstein died. And it was in all the papers that he could not finish his fabulous unified field theory, the theory of everything. A theory, by the way, which I work on professionally. Well, because of that, many people speculated what could possibly have been in that unfinished theory of 1955. Then an astronomer and also a writer on UFOs receives a letter in the mail stating that, yes, he was in the Navy, and yes, Einstein completed his unfinished work. It was a misnomer in the press. He actually completed the work, and the work talked about gateways and time machines and so on and so forth, and the person says that he witnessed things disappearing because of Einstein's unified field theory. Well, that person has never been tracked down. Most people think it was, in fact, a hoax. This entire story based on one letter referring to Einstein's unified field theory. First of all, I work on Einstein's unified field theory. That's what I do for a living. We even have a better version of it called string theory, which we think is the fabulous theory of everything. Does it allow for wormholes? Yes, it does allow for gateways into perhaps other universes, perhaps gateways into the past. But there's a catch. There's always a catch someplace. And that is, you can also calculate the energy necessary to create a gateway through space and time. And it is fabulous. It is the Planck energy. It's a quadrillion times the energy of our largest machine, the Large Hadron Collider based outside Geneva, Switzerland. In other words, the letter was a hoax. It was a clever hoax because it tried to piggyback over all the press coverage given to Einstein's unfinished unified field theory. So yes, we think we can finish that theory. Yes, it does allow for wormholes, but the energy necessary to open gateways through time is way beyond anything that could have been assembled in 1943, which is when the experiment supposedly took place, or even hundreds of years into the future. Good day.